And welcome back. We are progressing through Activity 9. In this video, we're going to cover Lesson 9.2, Translations. So that's what we're going to talk about today. So before we get too far, let's take a look at our learning targets. We're going to annotate those. We are going to circle our skill words. So our skill word is perform. We are going to perform translations on and off the coordinate plane. So we're going to perform translations on and off the coordinate plane. Then we are going to predict the effect of a translation on a figure. So we're going to perform a translation first on the coordinate plane, kind of see what's happening, and then look at what happens to it when it's off the coordinate plane. Just a quick refresher of Lesson 9.1. We're studying transformations, and under the umbrella of transformations, there are two different types of transformations. There are rigid motions, and there are non-rigid motions. So rigid motions preserve the size and shape under that transformation, and non-rigid doesn't. It's pretty simple. So today we're looking at one of those motions. Will determine whether or not it's a rigid motion or non-rigid. Hopefully you can think about it when we use the term translation. More than likely, you saw the word slide when you learned this in middle school. Hopefully you saw this in middle school at least a little bit. So let's take a look. We're still dealing with the marching band. So if you would draw a line at the bottom of the page, take some time to read the text. Also, check out the math terms and then play through the video to see how you did. So hopefully you took a second to read through the text. We see the marching band is doing something unique here. And so we're learning that our first transformation, called the translation, is actually a rigid motion. Notice the marching band in this diagram. After the transformation, it's still the same size and shape. All they did was literally move 2 yards to the right on the field and 4 yards up the field. And by its definition, a translation is when a figure, notice it says here, a translation as a figure really just slides it up or down, left or right. That's why I mentioned back that you possibly learned this as a slide back in middle school. So if this really is a transformation, then we should be able to represent that transformation as a function. That's what we learned in Lesson 9.1. And the function for a translation in this form is every point, xy, goes to x plus a, y plus b, in which a and b can be positive or negative. I highlighted that because we need to understand that on the x-axis, so let's write this, on the x-axis, moving to the right is positive, moving to the left is negative. So we could translate our figure to the left, and so a would actually be a negative constant. Likewise, for the y-axis, when we move up on the y-axis, that's positive. In this case, we moved up 4. That's why b was positive 4. But we could also go down the y-axis, and so we would see a negative constant. So I want to point out, just because we see x plus a and y plus b, doesn't mean a or b can't be negative. It all depends on the direction we're moving. So they tell us that the function here is technically, because they tell us a is 2 and b is 4, is that every point goes to or follows this function x plus 2, y plus 4. Which if you go back and look in the figure, what happens to it is we're really moving every point left 2 and up 4. Now, notice it tells us that a translation is a rigid motion in which every point is moved the same distance and in the same direction. Every point followed the same motion. What I think is peculiar is when we see this definition here, the actual distance and direction the translation moves is called the directed line segment, the actual distance and direction. And if you notice, here in the diagram, the directed line segment of the translation is shown by each of the arrows. So this right here, this what is really called a vector, it looks like a ray, is actually the directed line segment. The directed line segment. And it's shown here with all of these arrows that is how far and in what direction, hence the arrow, how far each of those points move through the translation. And we're going to see that, especially when we study translations off the coordinate plane, how important this directed line segment is. But without further ado, let's take a look at the chart here, the table. So the pre-image, recall the pre-image is the location of the coordinate or the image, or excuse me, the figure before the transformation. And the image is the location of the coordinate or figure after the transformation. So you might want to go back and make that notes before transformation and after transformation. So if the function really was every point goes to x plus 2, y plus 4, we're simply adding 2 to all of our x's and adding 4 to all of our y's, which again tells us that it's going to the right 2 and up 4. So Maria went from 2-4 to 4-8. Joe went from 3-7 to 5-11. Alfredo went from 1-8 to 3-12. And Lejeia, I thought this was interesting. They actually don't tell you where she began the pre-image. They tell you where she ended up. And so we can use that function in reverse. So if it's x plus 2, y plus 4, we can actually subtract 4 from 11 and find the pre-image, and we can subtract 2 from our x to find the pre-image of 5. So just a unique twist on figuring out that table. Remember, this really is a function table like you saw in Algebra 1, where the pre-image is your inputs, literally what you're putting into this function, and your image is your outputs. So if that helps you tie into what you learned last year in Algebra 1. Now let's continue. We're kind of seeing how the function of a translation works, kind of the path that a translation can move. If you would go and draw a line under number 2, don't move on to number 3. Pause the video, work through number 2, and also, I don't believe it asked for it, write the function. Write the function for the translation that's going on here. So you can put it over here. That's probably not the best point, but somewhere over in your notes, write the function of the transformation that is happening here before playing through the video. Okay, hopefully you're digesting through this text enough. We see that he directs the band member at 6:10, which is this coordinate here, to move to 4:13. So on this second coordinate plane, I wanted to show that transformation. I kind of used, this is the pre-image where it originally was, and this is the image in that darker gray. And this black arrow here, this is our directed line segment. It tells us where that point went. Now remember, if it really is a function, all of these points are doing the same thing. So number 2 says, for the band to move in a translation, how should each band member move? Well, they should move left 2 and up 3. So I asked you to write it as a function. Just a little practice there, writing functions of translations. So if it's to the left 2, remember that's a negative direction on the x-axis. But if it's up 3, that's a positive direction on the y-axis. So that's what the function would look like. I like this little math tip. Remember, if it really is a translation, it preserves the length and width of the figure. That's the definition of a rigid motion, to preserve the size and shape. So hopefully you're seeing how simple the translation really is. And so to test that, if you would, go and draw a line under the check your understanding. Complete items 3 through 5 before playing through the video. Okay, hopefully you took some time to work through it. On item 3, Maria's position at point 2-4. Her friend tells her that Maria's new position is described by this function since her new position is 7, 0. Well, that can't be. If this really is the function of the translation, if Maria was located at 2-4, we follow that function. 2, when we add to 3, we get 5. And 4, take away 2, we get 2. So if that really was the function that Maria used in the translation, then Maria's new position should be located at 5-2. Just looking at using the translation function, very similar to some of the ones we saw back in lesson 9.1. Now, item 4, I have a couple notes. If you need to use the function table, go for it. If you don't need to use it, go for it. Really, the way we're reading this is every point goes to x plus 4 tells us it moves right 4. Y minus 4 tells us it moves down 4. So every single point on this rectangle moves to the right 4, and moves down 4. And I did some color coding here, so hopefully you can see that. Likewise, on item 5, here is the function table for that. But x plus 3 tells us that it's going to move to the right 3. And when y does not change, that means it does not move up or down. So you notice that the triangle just simply moved to the right 3 units, but it did not move up or down. So use the function table if you need to, but if you're interpreting these translation functions with these directions, that is good too. Now, we've studied what it looks like for translations on the coordinate plane. We're looking at their functions. Now, the rest of the lesson, we're going to dive into what it looks like for a translation off the coordinate plane. So if you would, direct your attention, go and take a second to read this text. And actually, what I'm going to get you to do is stop right above item 6. So just read and digest the text. There's a little math term to help. Okay, so hopefully you took a second to read through this information. It can be a little bit confusing. A couple things I really want to point out. When a translation maps any point, and they use P here, and we see it's actually the center of our rhombus, but when they use a point P, when they translate it or it undergoes any transformation, they use P, and this little symbol is known as prime. So that would actually be read P prime. So we're talking about P where it ends up after the transformation. It doesn't become typically a new letter describing that point. So we just add this little, what looks like an apostrophe to represent where it's located after the transformation. So a couple things, translations can be defined without the coordinate plane. And that's where we start seeing all this crazy notation and such, is because we don't have the coordinate plane. We don't have these functions to define that translation like we did with the coordinate plane. So a couple things. When we talk about the directed line segment, we're talking specifically about 2 things: the distance and direction of the translation. And so recall that when we actually write 2 letters of a segment without the segment symbol above it, we're talking about that actual distance. And then I also want to point out when the directed line segment is AB, we're talking about from A to B. So we're talking specifically in that direction. So when we're using a translation, this is what the notation looks like. And you see here, I've added some notes to kind of explain each part. So the capital T tells us that this is a translation. We'll learn some other transformations and what those letters that represent it. Line segment AB is our directed line segment. That's where it goes in the notation. Point P is the point before the transformation, and the result, or what it equals, is P prime, or the point after the transformation. So the way I typically like to read this is P prime is the result of a translation of point P using the directed line segment AB. And remember, AB, the fact that AB is our directed line segment, we are going to move our translation whatever distance or length AB is and in the same direction as AB. I also put a little star here. From P to P prime, it's going to be parallel to AB. If you notice, all of these motions with our translations are creating parallel line segments. If you go back and actually draw, especially on this one, if you go back and draw connecting these, you actually see that all these directed line segments where the point moves or travels, all of these directed line segments are actually parallel to each other. That's what it's trying to tell you on our next page. So items 6 through 8 refers to this rhombus, which a rhombus is a parallelogram with 4 congruent sides. So if you don't know what a parallelogram by its definition is a 4-sided shape where opposite sides are parallel. And we typically use these arrows to show that the sides are parallel. So opposite sides parallel. And so a rhombus is a parallelogram where all of those sides are not only parallel, but they are congruent to each other. So that's what we're looking at here. And they also tell us that point P is the center of the rhombus. So now that you kind of have some context about what the notation looks like for a translation off the coordinate plane, let's perform the transformation. So item 6 says, draw this translation of the rhombus described by directed line segment AB prime, include P prime equal to, that's what we said, so the location of P after the transformation is a translation of point P using directed line segment AB. Now that's a little tough just using a pen and paper. So the next thing I'm going to show you is something called GeoGebra. So here's that same rhombus. Again, it's called GeoGebra. Let me see if I can write that on here somewhere. GeoGebra, believe.org/geometry. So if you want to do this on your own, have some fun with it. If you like this kind of exploration tool, go for it. Try it on your own. Draw this rhombus, perform the transformation, see what happens during the translation. So they tell us to translate this rhombus according or using the directed line segment AB. So if you're in GeoGebra and you've already created your rhombus, you're going to choose translate by vector. I used that word a second ago, translate by vector. That's our directed line segment. So the directions tell me to select the figure and then select the directed line segment or the vector. So if the directed line segment is line segment AB, I'm first going to select A, and then I'm going to select B and watch what happens. So what just happened, and you can kind of see that vector there from A to A prime, is we just shifted or translated this rhombus using directed line segment AB. Now AB was going kind of up to the right, so that's the direction that our translation went. So item 7 says which part of the rhombus maps onto BC. So let me back it up. If you lost where BC is actually here, the top right segment of a rhombus, and watch what segment moves or maps onto BC. It's actually A prime, B prime. So let's go back. Let's answer item 7. Which part of the rhombus maps onto BC? Well, that is A line segment A prime, D prime. And I'll kind of crudely draw it here. So what just happened is whatever distance and direction AB was, those points moved that distance and direction up to the right. So that C went here, C prime, B went here, B prime, A went to where B was located, so we call that A prime, and D went to where C was located, so we call that D prime. And of course, P is still somewhere in the center, we call that P prime. So they also wanted us to make sure we translate that center with it, so I just want to show what that looks like. So we're going to translate point P using that same directed line segment and see where P prime ends up, still in the center of our rhombus. The other thing I really want to point out, and one of the beauties of GeoGebra and why it's so great, is that it actually can do all the measuring for us. So if you look down here, I found the measurement from A to B, this segment of the rhombus. And it is roughly 8.9 units, whatever that is. So if this really is a translation, then the distance from A prime to B prime should be congruent because the translation is a rigid motion. And we know a rigid motion preserves size and shape. So I'm going to show you how to find the measurement. So if you find the measured topic here and click on distance or length, so I already found the distance from A to B. So now let's find the distance from A prime to B prime. And we see that it is also 8.9 units. So again, the translation is preserving the size and shape of our figure after the transformation. So one thing I want to point out, they also asked us to translate point P, the center of the rhombus. So I'm going to show you how to do that again for those that are taking the time to learn GeoGebra. So click on translate by vector. We're going to click on point P, the center. We're going to use the same directed line segment, AB, so click on it, and you notice where P prime ends up. In a very similar location in our image after the translation. The next thing I want to show you, and what makes GeoGebra so cool, is we were also told that a translation is a rigid motion which preserves size and shape. Well, we can kind of see that the shape is preserved. It still definitely looks like a rhombus. So what I would like for us to do is kind of see how it preserves the size. So I'm going to click on distance. I'm going to find the distance from line segment A to B, and we see that it's roughly 8.9 units. So this really is a rigid motion. Then the distance from A prime to B prime should also be 8.9 units. So I'm going to click on that segment as well. And we see that, yes, not only is the shape preserved, but the size is preserved as well. Now let's go back and take a look at our text. Now let's take a look at item 8. It says, identify a translation of the rhombus that would map exactly one point of the rhombus onto another point of the rhombus. So let's go back here. What really happened, if you think about it, is we took points D and A both, and we mapped D and A where C and B were. So we really essentially mapped 2 points from the rhombus onto 2 other points of the rhombus after the translation. So item 8 asks us, how could we create a translation that would map exactly one point of the rhombus onto another? Well, if we move left, or if we move at any diagonal, we're going to end up with the same result we saw here. So hopefully you're thinking that we could actually move these points up, or this rhombus, up, down, left, or right. And in fact, one of the easiest ways we can do it is we can actually translate this rhombus using the directed line segment AC, or A prime C prime. So I'm going to go over and show you what that looks like on GeoGebra. So let's actually translate. We're going to find the translating tool, translate by vector. So I'm going to select the figure, and then I'm going to select D, or it would originally be C, and we see that what happens is that it actually moves down. So we mapped one point, in this case C, onto point A from the original pre-image. So this is just an example of what a translation could look like, where we map exactly one point of the pre-image, in this case point C, onto one point of the image, which was originally A. This is just a basic idea of what that could look like. So now let's go back to our text and represent that using the notation. So now that we're in our text, we said that we could translate using line segment AC or line segment CA. So the way that would look is we use a capital T to represent translation, and we use the line segment AC or a translation along the directed line segment CA. Either of those would actually create or map exactly one point of the rhombus onto another point of the rhombus. Now, number 9 asks us to draw the following translations, show the pre-image and image, and label corresponding. It seems that they kind of just threw this word in here that you might not necessarily be familiar with. So corresponding points, we saw a similar idea to corresponding angles back in our parallel lines. So corresponding points are such that D is corresponding to D prime. Essentially, where does that point end up after the transformation? So A and A prime are corresponding points, P and P prime are corresponding points, and so forth. So it says, draw the following translations, show the pre-image image, and label corresponding points in each. So I'm going to show you how to handle this first one. Using GeoGebra, of course, it does say that it's translating 4 inches to the right, so feel free to use a ruler here and actually draw this. But I just want to show you using an online resource that we have. And I went ahead and changed it. Oh, I thought I changed it. Let me actually change these so it reads what you see. Thought I actually changed it. So it actually reads square ABCD. So let me get that fixed real quick. Okay, that looks a little better. So it tells us to translate square ABC 4 inches to the right. So I'm going to show you how I would represent that on GeoGebra. So I've created this line segment here that is 4 inches in length. And as long as I make sure that when I choose my directed line segment, I'm going from I to J, because that would be in the right direction, pun intended. And so I'm going to go down here to find transform. I'm going to select my square here, and then I'm going to choose notice that the arrow is formed here, and I'm going to choose the direction to the right. And notice what happens here. We get a square that's shifted 4 units to the right. Notice that the segments are still parallel to each other. This segment, line segment AD, is still parallel to A prime, D prime. BC is parallel to B prime, C prime. So really, we're just trying to understand and view what it looks like for translation of figures without the grid. Now, I'll also show you this, that you can, in fact, show the grid on GeoGebra to kind of see how it ties into the coordinate plane. So I'm not going to necessarily require you to do all these because it's a little bit tricky without them, but you can play with GeoGebra. If you would like to draw these on paper, really get cool with it, and do some exploratory work with it. So without further ado, let's jump back to our text. So 9 is all about translating these figures using these directions. And the last thing I want to look at together is the check your understanding. So take a second, draw a line if you would, draw a line underneath the check your understanding as you will complete the lesson 9-2 practice on your own. Take a second to complete items 10A through B before playing through the video. So the main reason I wanted to speak through this check your understanding with you is if you notice, what we're looking at here is the addition of these apostrophes. So after every transformation, B really does move to this point. And so to represent that, to show you where B ends up, we use that B apostrophe or B prime. Well, if we undergo 2 transformations, we use B prime prime, and that's literally how it's read, or A prime prime. So the more apostrophes you see after that letter or that point, that's how we read it, as primes. So if we undergo 3 transformations, we have points like B prime prime prime, C prime prime prime, and so forth. So I just kind of want to show you that there. So he plans 3 transformations in triangles in which point P is mapped onto P prime, and P prime prime prime, respectively. So literally P is mapped to all of these points. It says, which of these 3 transformations are translations? And explain your answer by applying the definition of a translation. So I wanted to draw these other points so you can visualize where these points would end up after these transformations. So for item A, I said the only ones that were actually translations are the transformation from P to P prime, and then from P to P prime prime prime. So hopefully you're seeing the reason why we didn't talk about this second transformation here is because it actually looks like this triangle was turned. We said that points after the transformation, all the directed line segments are going to be parallel to each other. For example, B went to B prime, that directed line segment, P went to P prime. So these 2 directed line segments I just drew are actually parallel to each other. But if we back it up a little bit and look from B to B prime prime, P to P prime prime, we see right here that these 2 directing line segments actually cross paths. That lets us know that this is not actually a translation because the directed line segments are supposed to be parallel. So you might want to add that. Directed line segments should be parallel. So we're not twisting or turning our figure at all if it really is a translation. Now, part B then says Maria stands at point P of the triangle ABC. To move to P prime, her instructions are to move 8 steps to the right. Do these instructions apply to all the other band members? Explain. Well, yes, in a translation, all points move the same distance and direction. So if they are to undergo a translation, then all of the points in that triangle should move 8 steps to the right. So that is the end of lesson 9-2. Hopefully you got to see a little bit of GeoGebra and how cool GeoGebra could be used. We might try to do some of it in class to hopefully help you understand how and some of the techniques you can use GeoGebra to, since we're really going virtual this year. Again, as always, go back to your learning targets. Go back and rank those depending on if your level of understanding increased. And as always, make sure you complete the 9-2 practice. Thanks so much. Hope this video helped.